got it. Yeah, and he's going to introduce some interesting stuff about the cigar and the Ricci soliton. Yeah, is that correct? All right.
Yes.
Okay, now I give it to you. Yeah.
Awesome, thank you. Yeah, so we're going to continue on with Ricci flow today, and in particular, we're looking at explicit solutions of Ricci flow. So last week we talked about spaces with constant sectional curvature. The first topic for today is Einstein manifolds, which can be interpreted as spaces with constant Ricci curvature. So let me just share my screen. Sorry, I should have done this beforehand. Here we go. All right, so let's begin with a definition. So a Riemannian manifold is an Einstein manifold. Is if the Ricci curvature can be written as a scalar multiple of the metric. So if we have Ricci G is equal to lambda G. Now, depending on who you talk to, lambda here might be a constant or a function. So I'm going to say it's a function for now. But really, for n greater than or equal to 3, we find that if we choose lambda to be a function, it actually has to be a constant anyway. It's only in n equals 2 that there's a distinction there. So now I'll just say where lambda is a function from m to r. So straight away we can actually calculate what this lambda is. So if I take the trace of both sides, so I take the trace of both sides. On the left-hand side, I get the scalar curvature, where on the right-hand side, so the lambda stays the same. And when I take the trace of the metric, I get the dimension of the manifold, which is n. So we can explicitly compute that lambda has to be the scalar curvature over the dimension of the manifold. Okay, so some examples. The first examples are actually the ones we discussed last week. So if a manifold has constant sectional curvature, then it's necessarily an Einstein manifold. So we have that these are each with their standard metric. So we have Rn, Sn, and Hn are all Einstein manifolds. Okay, but there are many, many more Einstein manifolds than there are manifolds with constant sectional curvature. So for example, if I take the product of any of these manifolds with themselves, then I get another Einstein manifold. So this is because, so I should write. So when I take the Ricci curvature of a product metric, I can write it like this. So if G1 and G2 are Einstein manifolds with the same constant, then the product metric, the product manifold will also be Einstein. So straight away, I can construct more Einstein manifolds from these examples above. The next one, I'm not going to get into too much detail, but I wanted to give an obvious, not an obvious, but an explicit example of an Einstein manifold that didn't have constant sectional curvature. So an example of such a manifold is the complex projective plane with its with the Fubini-Studi metric, which is its standard metric. So for those that don't know the complex projective plane, it can be defined to be the so complex numbers in Cn+1 minus 0, where we quotient out by if your complex numbers are scalar multiples of one another. So I'll just write it like this maybe. Now, so you can calculate that this has Ricci curvature equal to.
Hey, Jack, is that a complex scalar or real scalar?
I've written complex, but I think it should be real. Sorry about that. So that was a typo.
No, complex is fine. Complex is fine.
Complex is fine?
Yes.
Yeah, sorry, I wasn't paying attention. I didn't see you had actually written that, sorry.
Okay, I'm going to go back to complex. Okay, so yeah, so you can calculate the Ricci curvature and it's given by this. You can also note that CPN is simply connected. So by the previous week's argument, if it had constant sectional curvature, then it would have to be either SN, HN, or RN, which it isn't. So it can't have constant sectional curvature. So this is a non-trivial example of an Einstein manifold. So to remind everyone, this is really the equation that we want to find solutions to. So let's begin by assuming that our initial metric is Einstein. So G0 is Einstein. Now, since we know that Ricci G0 equals so S0 on N, where S0 is the scalar curvature of G0 times G0. A good guess, right, for the solution of our Ricci flow is to assume that G of t is just equal to some function of t times by our original metric. So we're going to make an ansatz that our metric is equal to lambda t G0. Okay, so let's see what happens when we make this guess. So we can do some calculations. So first of all, Ricci curvature is invariant under rescaling. So this lambda t here makes no difference to Ricci curvature. So we can just get rid of it, I guess. So we get Ricci G naught. But then since G naught is Einstein, that's equal to this. On the other hand, when we take a partial derivative of G of t, well, we just get a derivative of lambda, again with G naught. So Ricci flow is going to be equivalent to the following ODE. Also, if I write it all out like this, I have this equation, and of course, this means that this derivative has to be equal to this term over here. And we solve this to find the following. So this is our first solution of Ricci flow for Einstein manifolds. So some things to note. This solution, right, is homothetic, okay, by which I mean that it's a constant multiple of G naught, and depending on the time, depends on what that constant multiple is. So if we look at this, firstly, if we have zero scalar curvature, right, then this time is going to vanish and we're just going to get G naught. So in the case we have zero scalar curvature, sorry, we're going to have a solution of Ricci flow that's actually stationary. It doesn't evolve in time. So an example of that is in Rn, right? So if I say S naught equals 0, then G of t equals G naught. But now something interesting happens if, say, we have S naught is positive. So let me rewrite out. So if S naught is positive, then what we're going to find is that this term here is getting bigger. So eventually we're going to hit a point where this is 0. And of course, so we can't, the scalar multiple on the metric can't go negative because then this would stop being a metric. So this is actually, how we would interpret this is that our manifold is shrinking to a singularity, which occurs when, so we have a singularity at time n on to S naught. Right. Now the last case is if S naught is negative, in which case the manifold expands. So this this whole quantity here is getting bigger and bigger. So our manifold expands. So I should probably write that in this case we're shrinking, and in this case we are expanding. Cool. So this already gives us a bit of a clue as to how Ricci curvature can behave, Ricci flow, sorry, can behave. Now, at this point, I'm going to take a little bit of a detour to talk about curvature in very low dimensions, so in 2 and 3 dimensions. Because in these dimensions, we're going to get a lot of simplifications in our Riemannian curvature. Okay, and I guess maybe 3 dimensions is particularly important because Ricci flow was originally well, one of the big uses of Ricci flow was to prove the Poincare conjecture, which was a statement about, well, it was a statement in 3 dimensions, right? So let's start with 2 dimensions. So in 2 dimensions, our Riemannian curvature has only one independent component, right? So pretty much, in fact, of the 16, so the Riemannian curvature tensor, right, has 16 components. Most of them are going to be 0. And in fact, we can find that it's determined completely by knowing, say, this one component here. So of course, this is going to lead to massive simplifications as to how we can express the Riemannian curvature tensor. So I'm going to pull this a little bit out of the hat, but if we can find another 0-4 tensor that satisfies the same symmetries as the Riemannian curvature tensor and also agrees on this component, then we know that they have to be the same. Now, an example of such a tensor is the following. So we can check that these two actually have the same symmetries. And what this means is that up to a function multiple, they're the same. There should be. Okay. So something we note straight away is that, so we can take the trace of both sides. And when we do that, we obtain the following. So this straight away means that any 2-dimensional manifold, given my definition of Einstein, is, so this is an Einstein manifold, right? And we can also take the trace again to get 2f of p. And so we've calculated what f of p has to be. It has to be 1/2 times by the scalar curvature. We can actually also note from this definition that if we try calculate the sectional curvature, which in 2 dimensions we just called the Gaussian curvature, we can also calculate that f of p is going to be just equal to the Gaussian curvature. So maybe I'll write that. So of course, I mentioned before that in as soon as you have an Einstein manifold, it must have constant sectional curvature for n greater than or equal to 3. Well, we can see it's definitely not true in n equals 2, because every n equals 2, every 2-dimensional manifold is Einstein. So if it were true in 2 dimensions, it would mean that every 2-dimensional manifold has constant Gaussian curvature, which we know is not true, right? So the 3-dimensional case is more complicated than this, right? So in 3 dimensions, the Riemannian curvature has 6 independent components. Which is the same as Ricci. Now, this suggests, right, that as soon as we know the Ricci curvature on a 3-dimensional manifold, then we can determine its Riemannian curvature. So for me, when I was working through this, I didn't necessarily think that it was, I could believe it because they have the same number of independent components, but it didn't, just because they have the same number of independent components, it didn't seem obvious to me that they would, the Ricci would then determine the Riemannian. But in fact, you can check that this is true. And at least how I did it was I chose an orthonormal basis. So I used, say, normal coordinates. And then you can write your Ricci curvature in terms of the independent components of the Riemannian curvature. And then you can find that you actually get an invertible matrix. So you can invert those relationships to then calculate the Riemannian curvature in terms of the Ricci curvature. So anyway, what this means, if you do this computation and you check that this is correct, it means that if I want to find a special form of the Riemannian curvature tensor, I only have to find a 0,4 tensor that firstly satisfies all the symmetries of the Riemannian curvature tensor, but also agrees on its Ricci curvature. They have the same, when you take the trace, they agree. So similar to in the 2-dimension, I'm going to pull, in 2 dimensions, I'm going to pull something out of a hat. And I'm going to define the following 0,4 tensor. Now T here is a symmetric 0,2 tensor. So you can check that this has the same symmetries of the Riemannian curvature. Now it seems like a bit of a good guess in a sense once you know that it has these symmetries, because the number of components of independent components of T is 6, which is the same as the Riemannian curvature. So maybe the number of degrees of freedom that I have to pick this 2 tensor is the same as the number of independent components of the Riemannian curvature. So what I'm going to do is I'm going to actually suppose that I have that I actually do have that these are equal. And then I'm going to calculate what T has to be in order for that to be true. So how would I do this? Well, first of all, I take the trace of both sides. And so when I take the trace of the Riemannian curvature, I get the Ricci curvature. I'm of course using the summation convention. Now, when I take the trace, I'm going to find that because I've got these metrics in here, you're going to get a lot of simplifications. So as I work through, what I find is that, so the first term I get is T times the metric, where T is the trace of the 0,2 tensor T. And so of course, n equals 3 here, but this computation works in n dimensions. Like this. So we still can't quite determine what T is. But if I take the trace again, on the left-hand side, I'm going to get the scalar curvature. On the right-hand side, I'm going to get, so I'll get 3T here plus another T by the definition of T. So I get 4T. And what this means is that I can at least find what T is. So it's 1/4 of the scalar curvature. And then I can rearrange this formula here to find that I must have TJL Okay, so what I've done here is I've calculated this 0,2 tensor. So what we actually find is that in 3 dimensions, I can write my Riemannian curvature in the following form, where where this tensor is given by this linear combination of the Ricci and the scalar times by the metric. Yeah. Now, something to note here is if I'm in n equals 3 and also my manifold is an Einstein manifold, well, then what happens? So straight away, since M is Einstein, I know that Ricci is equal to this. And so therefore I plug this into my formula above and calculate that this Tij has to be the following. And then I substitute this back into this formula, which is equal to my Riemannian curvature. And I obtain that I can express my Riemannian curvature in this way. So something to note here is that this means that my sectional curvature is equal to 1/6 of the scalar curvature. Okay, but since I'm in 3 dimensions and I'm Einstein, I know I have constant scalar curvature, sorry, which this implies here that my sectional curvature also has to be constant. So in fact, if we're in 3 dimensions and our manifold is an Einstein manifold, we're actually in the constant sectional curvature scenario. Okay, so that ends the small discussion there on curvature in low dimensions. So finally, we get to move on to Ricci solitons. Now, I don't think there'll be enough time to get through all of it with the whole issue with the technology. So maybe I'll just give it a start and we'll work out what to do later. Okay, so really, from what I understand, Ricci solitons can be sort of looked at in two equivalent ways. So one way is as a generalization of Einstein manifolds. Okay. Now the second way, and we'll see that these are essentially the same, is that they can be understood as self-similar solutions of Ricci flow. And so that's how I'm going to introduce them as these particular solutions of Ricci flow. So before we can discuss Ricci solitons, we need to first talk about Lie derivatives. So a few definitions. So first of all, if I have a smooth vector field on M, and I also have a curve, theta, then an integral curve is the following. Sorry, so theta is an integral curve of x if we have the following relationship. Now, associated with each integral curve is a flow. So a flow is sort of a bit of a juggling of the arguments of your integral curve. So the flow associated with theta okay, so actually maybe I should say this in a different way. So I'm going to say that suppose for each point in my manifold, x has a unique integral curve. And I'm going to denote it by theta with a superscript p. And just for simplicity, I'm going to assume that it's defined for all time. Then the flow, okay, of x is the map. So theta subscript f, s, and it goes from m to m, and p gets mapped to theta with the superscript p evaluated at s. Now, something to note here is that theta 0 is going to be the identity from m to itself. So once we have these, we can define the Lie derivative. Of a covariant tensor. So the Lie derivative of a covariant tensor field T on M in the direction, also with respect to x, the vector field x, is the following. Okay, so it's the following time derivative, and I'm going to define what the star is in a moment. But in this sense, we can interpret the Lie derivative as another form of directional derivative. So we're taking the directional derivative in a sense of a covariant tensor field in the direction x. Okay, and so this star denotes the pullback of t with respect to theta. So it's given as follows. And then so maybe let's just take t to be a 0-2 tensor, because that's the only thing we're going to actually care about here. So say, for example, t could be the metric. Is given by the following expression. Like this. Okay, so how does this relate to Ricci flow? So with Ricci flow, we're wanting to find these particular solutions. Now, a property that Ricci curvature has, so firstly, we know that Ricci curvature is invariant under scalar multiples. So we saw earlier with the Einstein case that if I assume that my solution is lambda of t times by the original metric, then that lambda of t disappears when I put it into the Ricci curvature. Now, another property of Ricci curvature is it's invariant under diffeomorphisms. So what I mean by that is that if I have a metric and I have a diffeomorphism phi, and I want to calculate the Ricci curvature of this, then in fact, I can just pull out this, the pullback of phi like this. So Ricci curvature satisfies this, sorry, not Ricci curvature, just, Ricci curvature satisfies this property where phi here is a map from M to M, and we'll say it's a diffeomorphism. So then the idea is to guess we have a solution that looks like this. So I'm going to take firstly a scalar multiple, and then I'm going to take a the pullback of G naught, our initial metric, with respect to some diffeomorphism, and the diffeomorphism is allowed to evolve in time. Okay. So this is what we call a Ricci soliton. Okay, so now let's see what happens if we actually substitute this guess into Ricci flow. So on one hand, so if I put this into the Ricci curvature, so as I said before, this guy disappears because Ricci curvature is invariant under scalar multiples. Then using this property here of Ricci curvature, I can pull this out the front and get this expression. Okay, so that's the right-hand side of Ricci flow. So now what happens to the left-hand side? So that's the time derivative of the metric. Okay, so we can apply the product rule to this expression. So firstly get sigma prime of t times this term plus now I'm gonna be careful here. So then I also get this term as well as part of my product rule. So let's try simplify what this term should be. So now the first thing I want to do is actually make a change of variables. So I'm going to set tau tilde to be tau I want it to be tau minus t, right? So then I can rewrite this expression as tau tilde equals 0. Like this. Now, the next thing I do is I use that I can split these two up. And when I do that, I also use that then the pullback, that's a t, is given by the following. To get the like this. So now the point of this computation is now this term here doesn't depend on tau. So I can pull him out the front. And then this with this is exactly the definition of my Lie derivative here if psi is generated by some vector field. Now I'm running out of time, so I'll just finish this off and we won't actually discuss anything further. So this is precisely this expression here, where y of t is where psi is generated by some vector field y of t. Okay, so maybe to just finish off, the point of this exercise is that if I assume that my metric is of this form and I plug it into the Ricci flow equation, then what I obtain is that my initial metric must satisfy the following relationship. So on the left-hand side, I had, so I had this plus this times by this. So I had sigma prime and on the right-hand side, I had this. Now, at this point here, if we assume further that our sigma has the following form, then we actually get, and if we also assume that our vector field y of t is given by 1 on sigma of t times by x, where x is some fixed vector field on M, then what we actually find is that we get the following expression. So on the left-hand side, it simplifies to this. So here, I should say lambda is in R. And on the right-hand side, I get this. So what we really want to look for in order to obtain a particular solution to the Ricci flow is G naughts that satisfy the following equality. For some vector field x, okay, and some constant lambda. So this is the other definition that you often see. And if, in fact, if you Google Ricci solitons, this is the definition Wikipedia gives. And so you can see that if G naught satisfies this equality, then from that, we can generate a solution of this form to Ricci flow. Okay, so it's important then to try find particular solutions to this equation. Okay, so I was going to go through an example, but we've run out of time, so maybe I'll leave that there. But thanks everyone for listening.
Thank you very much. It's a pretty, yeah, it's a very good talk, and especially the detailed competition. I mean, I myself learned a lot, so thank you very much.
Well,
and does anyone else has a question or comment? Glenn, you want to add up something? Or Paul?
No, it was Jack. It's a good job, and in the face of technology that won't cooperate, very good.
Yeah, that was really annoying. Hey, sorry about that, but yeah, quick fix though.
It's all good.
Yeah, it's pretty nice.
Yeah, thanks very much, Jack.
That's all right. Thanks for having me.
Okay, so are you going to continue with the discussion next week? The same topic?
next week we'll have Shintao Lua is going to
Oh,
speak about short time existence and uniqueness, actually.
Okay, sure. Yeah.
All right. See you then.
Yeah. See you next week.